Hello, welcome to Integrated Engineering Software's first webinar on visualization techniques. My name is Dennis Peterson and I'll be conducting today's webinar. I'll be using a few slides to start with, and then I'll demonstrate how to create visualizations using our 2D and 3D programs. Now, we decided to do our first webinar on visualizations, and we thought that visualization would be a topic that's of universal interest. Visualization of field analysis results is extremely helpful in analysis. Sometimes you need just a force or a torque calculation, but often you want to see a field distribution. And also, if you have good visualizations, good plots, they're very effective in technical communications and in presentations. So we're going to start off by demonstrating some basic concepts because these are key, and then I'll go into some demonstrations of the advanced features, things like profile plots and isosurface plots and animations that perhaps are not used as much as they should be. So we'll begin by using a quadrupole magnet. I've got both 2D and 3D versions of this and other 3D models as well. The quadrupole magnet is very common in the accelerator industry, and in fact I'm using this model for some Lorentz models that we'll be using in our next Lorentz brochure. So you can see I've made a periodic model. I've only modeled 1/4 of the magnet. In fact, it's anti-periodic because the poles alternate in polarity. So the first concept, which might seem very fundamental, is often overlooked, is that in order to create a visualization, we first have to have sample data points throughout the model space. It may be throughout the whole model space or just a restricted portion. And I've shown here a scatter plot of the B field in the quadrupole magnet, and this is deliberately a coarse scatter plot because I just want to emphasize, again, you're looking at just discrete points. And often the question comes up from our customers. They say, we're interested in maximum field values, and we did a contour plot, then we zoomed in or we changed our program window and the maximum value changed. Well, if you think of this grid of points, it becomes obvious why that happens. If you have a coarse grid or you're zoomed out, it's pretty much a matter of luck as to whether or not you're going to have a sample point close to a point in your model which is generating the maximum field. I have, in fact, a magneto model which has two scatter plots. One is a zoomed out coarse density plot, a very coarse grid, and also I have, if we zoom in, a second scatter plot. You notice that the dots are a lot smaller and they're of a finer density, and also you have more of the sampling points close to this arc, which is where the maximum fields occur. This is just a fact of the way contours and other visualizations are created. So in fact, if you wanted to find the exact point where you have the highest field, you're probably better off actually doing a graph along the segment. That'll give you a sampling right on the boundary there. So the next point is that you can locate your sampling grid at different points in your model space, and that might be very helpful. Instead of having a grid that spans the entire workspace, you might want to just restrict it to a smaller area. So here I've shown a sampling which is done in the pole and the back iron, and we're not at this point concerned with what the field is in the air gap. And this would be useful if you're concerned about saturation of the steel. Location of the grid is relatively simple and straightforward in the 2D program. In 3D, you have to deliberately specify where you want the grid because in the three-dimensional viewing there are more options. And the final basic concept is that once you have your grid points, then we have to do some kind of an interpolation connecting the grid points with contour lines and filling the space with between the contour lines with some sort of shading. And so here I've shown a solid contour plot in Magneto. So now that I've gone through these basics, we'll go into looking at actual 2D and 3D models and how you would create plots for them. So I'll again return to a Magneto model. So here's our quadrupole, and I'm all set up to do a field line plot. And just to show, again, on the 2D program, your choices of location are limited. You can do a plot on the plane, which means basically the view window that you currently have, or you can specify on a region. So in this case, let's do a field line plot. And that gives you a very good indication of the periodic nature of the model. And you can choose to use different underlays. Here we just have the outline. You might be interested in looking at how the elements are distributed. You might want to make a presentation with the material shaded. You might want to see if there are the volume sources or permanent magnets. So you have those options. Now, let's say that we are interested, as I was talking about before, with the flux density in the iron parts of the magnet. Let's restrict ourselves now to a region plot, and once again we'll do a fine density contour plot. I'll click the new plot button, and I'll pick this region, and I'll change that. That's just colored lines. I'll make it a solid color. So now you have a good indication of where your highest field values are. You can see they're the dark red color, and the blue color would be very low flux densities. So that all makes sense. Now I'll show you a 3D version of this magnet. So here I've created a rather short version. It's not very long. And we're showing again it's a periodic model, so we've only modeled 1/4 of the magnet, one pole. Now in visualizations in 3D you have to specify the location where you want the plots to occur. Also you'll find in 3D models you often find a better plot if you can hide parts of the model that aren't of importance to you. Like right now I'm not really concerned about these coils. So here we have, just to show you, we have volume currents defined in these volumes, but they obscure the parts of the model that I'm most interested in. Now, I've defined the coil regions or coil volumes as an object, so I'm just going to hide those volumes now. Okay, so now they're out of the way, and I'll go on and start doing some plots. So with the 3D viewing space, you're looking at a projection on a two-dimensional window of a three-dimensional space, and you can specify, depending on the type of plot you have, different types of options. So for instance, we could have arrows plotted on a plane, on a surface, in a box, or in a volume. In this case, we have a volume already made for us. We have the pole piece, so let's just do that first. Let's do, say, a coarse density arrow plot inside. Okay, and you can see they have a nice solid rendering in 3D of the arrows. You can see they're color-coded according to the magnitude. And I'll just delete that now. Okay, now let's say that we wanted to do a contour plot. We have to specify a component. In this case, I'm going to specify the Y component, and I'll do, say, a medium density plot, and we'll plot it on a plane. Now, the difference between 2D and 3D is that you have to specify the coordinates of the plane. So in this case, I know the coordinates that I'm interested in. My first corner point will be at x equals 0.3, y equals 0, and z equals 0. The next corner point will be at x equals minus 0.3, y equals 0, and z equals 0. So notice now it's drawn a line. And so the last point that will define that plane will be x equals minus 0.3, y still equals 0, but this time we're going to have z equal to 0.5. Okay. So you can see that in the air gap, in the middle of the air gap, there's a nice gradient of the field, which is basically the way quadrupole magnets are designed to function. Now you notice that I had to specify the corner points of the plane. We could also just pick a surface, okay, for plotting. And one of the key techniques, which is very useful and simplifies your work when you're doing three-dimensional plots, is to create reference geometry. So in fact here, I'm going to show you that in this model we have an extra surface defined. We have a circular surface which I've hidden, and now I'll display it. And this circular surface has been constructed so that it passes right through the middle of the pole, and also it covers the airspace between the poles. And that does no harm because we haven't assigned any physical properties to the surface. It's just there for the convenience of plotting. So now I'll use that surface to plot arrows. Okay, and I'm even going to make these arrows a bit bigger. I'll double them in size. And maybe that's a little too big. Let's make it 1.5 instead. Okay, I think that's a good plot. So now as you rotate the model, you can see how the arrows are being plotted in the image regions where we have the other poles, as well as the actual geometry pole that constitutes our model. Now something else we could do, you'll notice that I constructed the circular surface so that it cuts midway through the pole. Because this pole also has a symmetry plane, we could reduce this magnet model even further. We could cut it in half again and just model half of the pole and half the coils. And in fact, that's what I've done in this next model. So I'll just rotate it. So you can see by using, again, this is an anti-symmetry plane. We've cut the model in half, so we're only modeling half a pole. And that actually makes things easier. I do this quite often when I'm creating plots. Whenever I have sort of symmetry conditions, I use those. That makes the model solve faster. And also, it means there's less work in hiding different parts of the model when you want to make a plot. And you still have the front part of the model which shows you the actual geometry. So here again we would have, say, a surface that we wanted to. If we wanted to plot the B field contours, we could do it on this surface. And also, for this same model, I still have that same circular surface. Now, if you're familiar, as you are, I'm sure you are with our modeling rules, normally we don't allow overlapping surfaces. When you have two objects that are touching each other and they have their two surfaces are touching, that's generally not allowed. But again, there's no physical substance to the plotting circle. It's just there for convenience. So that causes no problem, even though it's overlapping part of the pole and part of the coils. Because there are no physical properties, it doesn't interfere with the field solution at all. So now I'm going to plot very coarse contours of the vector potentials. Okay, this is sort of equivalent to field lines, the field line plots that we do in Magneto. What you do, you plot the normal component, and in this case, the way the plane is oriented, the normal component is actually the z component. Sometimes you have to use the normal component calculated on the surface, but in this case we can just plot the z component. And now I'll just select, you notice here I'm selecting the surface. If I select up here, I'm selecting that pole, but I want this whole circular surface. Okay, now I deliberately did a coarse plot because I wanted it to solve very quickly, but I've actually made even finer plots, and now I'll introduce another new feature. I'll show you our output manager. So I'll delete the plots here. So far I've been using the field results dialog box, but back a couple of versions ago we introduced the output manager, and the output manager has a couple of advantages. Okay. First of all, you'll notice that we have two types of plots displayed. We have the vector potential plot, and we also have a flux density plot, this sort of solid or semi-transparent shading. And that's something you can't do with the field analysis results dialog box. When you switch plot formats, when you're going from, say, a contour plot, a flux density, to a vector potential plot, it's either one or the other, and you've lost it. And also, if you don't save your model with the plot, you've lost the plot. With the output manager, you have those plots saved until you delete them or you clear the data. Something else I'll show you. Open the output manager again. If we look at the properties of this flux density plot, you'll notice it has a transparency setting. I'll remove that transparency. And now you can see that you have a more solid view of the flux density plot, but it now interferes with the viewing of the vector potential lines. So I'll just put that back again just to show you. Using transparencies in plots is also a very helpful technique. About there it was, I think. Roughly there. Now, as I mentioned, using the output manager, you can combine plots, which is something you can't do with the field results dialog box. So I'll just show you how to define an output, and we'll add another plot at the same time. You go Solution, Define Outputs, and it shows the ones that are already there. And you can add results, things like force calculations or field samplings. In this case, we'll add another plot, and I'll add an arrow plot. So we'll click on arrows. We'll have the B field. It'll be on a surface. We'll make it a medium density plot, and I'm going to restrict the scale from about 0.1 to about 1.4 Tesla. I want the solid cones. I'll use 16 colors, and the rest of the settings are good. So now I'll click on the New Plot button, and we'll pick this surface. And there we have now the arrow plot. So we have three different types of plots displayed. That's a lot of information being shown in one view. Also, once you've put these settings in the Define Output box, every time you modify and solve the model, it'll generate another set of these plots as well. And just rotate the view a bit so you can have a look. So now we have the B field arrows, which are showing the direction of the field and to a certain extent the magnitude. We have the vector potential lines, which give you an indication sort of like field lines. And we have the flux density. And that's all been done in one plot. It makes, I think, an interesting picture. Now, the next thing I want to show you are some more advanced plotting features. I'm going to show you the profile plots, which is, again, something people probably haven't used very much. So profiles are basically a three-dimensional plot where the data is sampled on a plane. So what you're seeing here on this plane, which is cutting the coils in half, we have our standard contour plot of the axial component of the field. And that sort of gives you a color-coded representation. But you could also give it a three-dimensional nature if you take the contour values and you use that as a distance value in the direction normal to the plane. So where it's red and positive, that means you're plotting a value on the surface which is in this direction, which is in the positive direction. And if we rotate it around, you can see where the axial component is negative, where it's blue, that plots below the plane. Now I'll show you how to do a profile plot. First, again, I'm going to have to unhide a surface. Okay, I picked the wrong surface there. Hang on a second. I'll just reload this file. Okay, so let's switch to a wireframe view. And let's reduce the size. And now let's show that surface again. This one here. There we go. Okay, so these will give me my reference points for plotting the profile plot. So now I want to do a B-field profile plot, very fine density, the Z component, and you can only plot profiles, the grid location is restricted to the plane. So now I'll click on the New Plot button, and then I'll pick these points. Alright. And you notice that my previous plot I'd made semi-transparent, whereas this new plot has no transparency setting, but we can change that. Using this, there we go. And again, that gives you sort of an idea. Mainly with Helmholtz coils, people are interested in the uniformity of the field along the central axis. Now, another advanced feature I'm going to show you will be isosurfaces. And if you saw some of the videos we've been doing lately on visualization techniques, you may have seen this model already. Basically, this is mushroom electrodes. People in the high voltage industry use these for testing oil samples for breakdown. And I've shown voltage contours plotted on a plane between the two electrodes. The red electrode is at positive 1 volt, the blue is at minus 1 volt. Now you notice there's a semi-transparent volume here, and again I just have that because it is very convenient for me to have reference points to use the corners when I'm plotting, say, a contour plot or an isosurface plot. I'm going to change the transparency of this volume though, so that it's just barely there, so it doesn't interfere with our view. We're just using this for references. So now we'll do a profile plot, excuse me, an isosurface plot, and we're going to restrict the range between minus a half and plus a half volts. And you can only do isosurface plots in a box. So now I'm going to click the New Plot button. Oh, we're still in the transparency command. There we go. Okay, now we pick the different corner points. So this is a lot easier than generating the points using the keyboard. And here you can see what the finished isosurface plot looks like. Basically, isosurfaces are an extension of contours into three-dimensional space. Now, the last thing I wanted to show you was animation of plots, and that's very useful in the case of parametric analysis. So what I've done here, I've created a parametric which varies the length of the pole, and I'll show you by doing a validation what happens in that. I've already actually run this, okay, so at each step of the parametric we're going to get a contour plot on our circular surface as before. And I've already done this animation. And this is what it looks like. So remember earlier I mentioned that quite often people who are familiar with our 2D programs find it kind of disconcerting when they see the vector potential lines in 3D. They expect it to look like the field line plots. And the answer to that is that they will look like the field line plots if the model is long enough. We can even speed this up a bit. Generally, animations are very effective when you're doing a demonstration for customers. They find it very interesting to see how field results change. Okay, now that basically finishes the formal portion of our presentation. And so now I'd like to answer any questions you might have. If you haven't already done so, please type your questions in the GoToMeeting panel, and I'll try to answer them. Any questions which are very long I can answer afterwards, perhaps by email. So if you do have any questions, please type them in now. Okay, the question's been asked is whether we're using IES CAD or other CAD to make these models. These models were created entirely either in Magneto or Amperes or Coulomb. You could have created them, I guess, in the other CAD tools, but I'm so much familiar with our own programs that I build them basically just from the start. I don't bother using CAD tools. We could save these, I guess, as step files. The advantage of using our own CAD tools, the built-in tools that come with the programs, is that then we know that the geometry has been constructed properly. The current winding, I could show you that. Yeah, basically it all started from the Magneto file. See, basically what I did, I started from this Magneto model, and then when I opened it in Amperes, I had these surfaces, and basically I just built it by sweeping. Okay, well, now I'm sure that probably there'll be more questions after you've had a chance to review the video of this webinar. So feel free afterwards. You can always email us questions. So with that, I guess I'd like to thank all of you for taking the time, and hope to see you all again in our next webinar.